Okay, Geometry A students, we are going to be going through the Semester 2 review as a walkthrough. I will not be doing every single problem. I will be doing many of them and talking through the technique for the solution. So if you're just here to copy down answers, you won't get them all, but hopefully you'll get enough to figure things out. All right, from Unit 4, Part 1, which we began during the second semester, one of the key ingredients that we talked about was similarity, and similarity between all sorts of shapes, whether they're polygons, convex, non-convex, it didn't matter. And one of the key ingredients is to always make sure that you are comparing two sides that belong together. Now on this first triangle, since it is a right triangle, I've got two right angles and two congruent angles. These two triangles would automatically be similar by angle-angle similarity. But the question asks us to use what you know about similarity to solve for x. So I'm going to set up a proportion, which is two fractions that are equal to each other, that compares like quantities. So on the left triangle, the 16 is the hypotenuse, and I'm going to compare that to the right triangle's hypotenuse, which is x. And then I want to make sure that I always stay going from left to right, or big to small, or top to bottom, or left to right, or whatever comparison I'm making. And so since I went from the left triangle to the right triangle, I want to make sure I do that each way. Now I'm going to make use of the cross multiplication property, where I multiply the bottom left side up towards the top right and vice versa. And so I have 12 times x on the right side and 9 times 16 on the left side. And now it's a simple matter of solving that the rest of the way. Divide both sides by x, and I get x is equal to 12. And that makes this hypotenuse 12. Now as I look over at the number 4, which will be the next problem I'm going to do, I can see these two pentagons that I'm told in the problem are similar. So I'm just going to believe that they're similar. But one of the things that I want to make sure I match up is that this angle here matches with that angle, and the other angle, the single rainbow one, is right here. So that means that the 8 that is between those two colored arcs must match up with the x. So if again I'm going to go from left to right, I'm going to compare the 8 to the x. Now the only other number I have on the right triangle, or the right pentagon, I'm sorry, is the number 10. And that will match up with, let's see, if I go away from the purple towards the red, and then past one blank side, I get to the 10. So I go away from the purple towards the red, keep going past that one side, and I get to the 6. That tells me that the 10 and the 6 go together, but the 6 is on the left and the 10 is on the right. So it's got to match up like this. So this particular question is really designed to tell me whether you know which sides go together, and whether you can reason that information out. I'm going to let you finish that one and make sure that you get it correct. And maybe at the end of the video I'll go back and check to make sure you've got it right. We'll see. Alright, let's move on to number 5. And in the problem for number 5, they give me this similarity statement. And this is an important skill for you to be able to read a congruence statement or a similarity statement that tells me that the P and the J match up, and Q and T would match up, and likely R and L will match up as well. So now as I look at this, I'm going to go with P was the first letter, then Q, and then R. So then J is the first letter, then T, then L. So that means that this 24 right here, connecting 1 and 2 together, must match up with PQ. And from 2 to 3 is the 12, and that would have to match up with the X. And last but not least is the 3 to 1, and 3 to 1. So now I've got these things color-coded by how they match up to each other, and I'm ready to either answer the questions or do some more thinking about this. Letter A says, based on that similarity statement, which side matches with JL? Well, now that's an easy choice. JL is in blue on my paper, connecting 1 and 3, so RP. So my answer would either be RP, or, since the order is not going to matter, I could do PR. Either one would be acceptable. If it was a multiple choice question, you'd have to be on the lookout for both of them. Letter B says, set up a proportion to solve for x. Well, I know which things match up. I'm going to go from the left triangle to the right triangle. So I'm trying to solve for x, so I'll put x, which is purple, compares to the 12. And the only other pair of numbers that I really have on the left triangle is the blue one, the 8, and that matches up with the 22. Here again, I'm going to cross multiply. So I bring the 8 times the 12 and the 22 times the x. And let's see, I believe that 8 times 12 is 96. So I'm going to divide both sides by 22. And let's see, 8 times 12, yep, 96 divided by 22. Oh, there's a number only its mother could love. X is going to be around 4.36. And I would like you to include a couple of decimals as you do these types of problems. Okay, moving on for number 6. Using the triangles to the right, answer the following. Triangle CAT is similar to triangle, here the whole reference is about can you match up things that belong together. So I'm going to start this one by following CAT. That's angle 1, angle 2, angle 3. I'm going to pause for a minute and let you figure out what the proper answer should be and see if you get it right. Okay, so I'm going to match these things up. Angle 1, or number 1, has a double rainbow, so this must be the first vertex. Angle 2 is blank. Angle 3 has the this symbol on it, so that must be angle 2. So going in that same order, G, D, O is how they match up. And since I'm not given any side information at all, I would reject all of these and leave behind only angle-angle similarity, which is one of the most prevalent and easy ways to prove two triangles are similar. I'm going to do some of these, B through G. Now this symbol right here is the angle symbol. It says angle CAT, so that means I'm going with angle. It's the number 1, the number 2, and the number 3 on my picture. So over here it must be angle GDO. And letter C says angle O corresponds to, angle O is right here. That's got the rainbow with the double hash mark, so it must be angle T. And I'm going to do one of these 3 down here, E, F, G. Let's see, I'll go with letter F. CT, which is going from the number 1 to the number 3, means that I need to go from the number 1 to the number 3. I would take GO as probably the easiest answer. Now, you can also do that same information without a picture if you wanted to look back up at the similarity statement where I'm going from C to T. That's the first and the third letter, so that would take me from G to O. Same answer. Either one is fine. And like before, the order doesn't matter, so I could take OG as a possible answer. I'm going to let you do those other ones and check them on your own. Number 7, which similarity theorem can show that P and W, okay, let me look at those, P, N, W, okay, so that's this purple triangle and PTV, okay, so that is an outside, oh, that was nicely drawn, that is this outer big triangle. Which similarity theorem can be used to show that these two triangles are similar? Well, we had some choices that we could use. There was the side-side-side similarity, there was angle-angle similarity, there was side-angle-side similarity, and remember, when we see these S's here, that means that the sides are proportional, have the same ratio. So let's see, proportion, oops, okay, fine, you can stay there. Let's see, side, 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 angle, angle, side, angle, side. There was also a, you could do angle, angle, side, although you don't really need that because once you have the two angles, it's the same as this guy. We've got side, side, side. Excuse me. Once again, we could do angle, side, angle similarity, but again, we've got two angles, so it's really the same thing as this guy. So I hardly ever use those, although they're legitimate. They're real. So I'm going to let you take a minute and see if you can decide which of these three are going to fit that picture the best. And one of the key ingredients is that the triangles overlap. That is a very important fact. Did you get it? Did you figure out what the key ingredient was because the triangles overlap? They overlap right here at angle P. So on the purple triangle, I have this angle with a single rainbow and a hash mark and a double rainbow. And on the red triangle, I have the single rainbow with a hash mark and a double rainbow, which means the correct theorem is angle-angle similarity. That would be the easiest one. All right, now number 8 is talking about two different triangles that are not referenced over here. So that is for a brand new problem, and there's no picture. That means you're going to have to do it all from reading this statement. So I'm going to just do a couple of selected parts of this, like I'll start with letter C. Angle WOL. So WOL starts here, goes to there, and then to there. So I want to follow the exact same pattern to find the angle that's going to match to that without a picture. So it's going to be angle TIS. And it would have to be in this order this time. It cannot be in any order you want. Excuse me. How about side TS? Side TS, let's get rid of all those things. Side TS is the first and third letter, so it must go with WL. And I will let you do the rest of those. Number 9. In the following diagram, AB is perpendicular to AD. AB is perpendicular to AD. Well, perpendicular means forms a right angle. And that is always a key fact. So I'm going to write down 90 degrees right there. They also tell me that AB is parallel to DE. AB is parallel to DE. Symbols for parallel lines are these arrows. They can be a single pair of arrows or a double pair, or get an eraser that erases some things. There we go. And they tell me that angle 1 is equal to the measure of angle 2. So that means these two are the exact same size. I don't know how big they are, but I know they're the same size. And again, the question is, which similarity theorem can be used to show that the two triangles are similar? That ABC is similar to DEC. Okay, so my choices, as before, are side-side-side similarity, side-angle-side similarity, or angle-angle similarity. Well, I always still like angle-angle similarity the best, so I'm going to see if I can figure out a way that that would work. Well, I do have one pair of angles that are congruent, but I don't have another one yet. Here's kind of another clue. I don't have any information about the sides at all. So I'm starting to feel like there's not enough information to show either one of these two as a possibility. So I'm going to think a little bit about these parallel lines and the things that I remember about parallel lines. And since most of us are most familiar with parallel lines looking like this, I'm going to make some excuse me, some references to that picture. Like, I remember that these guys all are going to be congruent. They're corresponding angles. This one and this one are corresponding. This one is vertical to this. These two are alternate interior angles, and these two are vertical. These guys are corresponding. So that's why all four of those are going to be the same, only when oops, I left off the parallel symbol. Only when the lines are parallel. Now these two are going to have to be the same, just like those two, and those four. So I've got two sets of congruent types of angles. Now, one of the other key pieces of information is that these guys together are going to be supplementary, which means they add up to 180 degrees. And that is one of my key ingredients. So even though this picture is drawn sideways, I'm going to draw my parallel lines here a little bit longer. And you can see I've got this transversal that's coming across right here. And suddenly I can start to see what things have to be congruent. Like this 90 degrees that's right here in the corner would have to match right here. And these same two would have to match up over here in the exact same way. So this has to be 90, and this has to be 90. Now the cool thing about 90 degrees, when they make a little four angle pair like that, is that if one of them's 90, they're all 90. So that means that this is 90, that's 90, this is 90, and that is 90. Now going back to our two triangles, where I have this big blue triangle here and the big green triangle over here, now I can see that I do have a pair of angles in each one. I've got a right angle, and I've got that congruent pair of angle 1 and 2. So now I'm for sure their answer is angle-angle similarity. Number 10 talks about slopes and how they relate to parallel and perpendicular. Now perhaps you will recall that when the slopes are equal, the lines are parallel. And if the slopes are, and here we go for some big words, are negative or opposite, reciprocals. Reciprocal means it's upside down. If the slopes are negative reciprocals, then they are perpendicular. That's the symbol for perpendicular. If they're anything else, then they're just lines. They cross each other, they intersect, they go on diagonals, whatever, doesn't matter. So for number 10, part A, if the slope of the line is negative 4/5, then the slope of a parallel line will be, anyone? Anyone? Yes, that's right, Mr. Hampton, negative 4/5, the exact same slope. For letter B, what's the slope of a perpendicular line? Well, it's got to be the opposite sign and a reciprocal. So it's not going to be negative, it's going to be positive, and it's going to be 5/4. Letter C says what's the slope of a line that's parallel to this equation, that linear equation? Well, the first thing you got to know is what's the slope of that linear equation. And perhaps you will remember that when it's in this form where the y is all by itself and everything else is isolated on the right, this guy is the slope. So I'm going to let you answer letter C as if the slope is 3/4. Alright, Unit 4, Part 2, Trigonometry. Probably one of the most important units that we do in geometry because the sine, cosine, tangent, law of sines, law of cosines, all very important. So off to the side here, I am going to write down the mnemonic that I remember for SOHCAHTOA. This only applies for right triangles. Don't try to use it if it's not a right triangle. The law of sines was the sine of the angle over the side opposite that angle, and the sine of an angle over the side opposite. And the law of cosines is a little bit harder to write down in terms of words, but if I'm going to use a little letter squared like b squared, then that means the ending of this thing is going to be the cosine of angle b. And then the other letters, a squared and c squared, kind of feel a lot like the Pythagorean theorem, except we don't care whether they're letters a, b, and c. I do know that this guy and this guy are the same, and these two are the same, but these guys aren't squared. And that -2 is just always there. Alright, so that's my little review for what those formulas are. And now I'll solve a few select problems here. So let's see, I feel like starting with number 11. As I look at number 11, they gave me this 38 degrees. It is a right triangle, so I can use either SOHCAHTOA or my favorite, the law of sines, but you can use either one. As I look at this, I'm going to do one with the SOHCAHTOA just for the fun of it. The 38 degrees, that x is the opposite side. The 15 is the hypotenuse. That leaves this blank side to be the adjacent. So I need the trig function that will connect the opposite and hypotenuse, which is, anyone? Yes, that's right, the sine. So I'm going to be doing the sine of the angle, 38 degrees, is equal to the opposite side over the hypotenuse. I need my calculator for this. I'm going to end up cross multiplying. So I have 15 times the sine of 38 degrees equals x. In my calculator, I am doing 15 times the sine of 38. Uh-oh, I better check something. Always want to make sure that my calculator is in the right mode. Okay, radians, degrees. I want degrees. That's good. It's highlighted, so I'm okay. If I'm in radian mode, all my answers are going to come out wrong. So 15 times the sine of 38 is 9.23, which fits. The 15 hypotenuse should be the biggest side, without a doubt. So 9.23 is the value of x. I'm good to go. Alright, so I'm going to try my hand on number 13 using the law of sines, because I like the law of sines. So on that problem, I've got my sine of 41 degrees, and opposite of that is the letter x. And the only other angle that I've really got handy is the 90, and so I can do the sine of 90 over 23, since the 23 is opposite. I cross multiply with these guys, and I get 23 times the sine of 41, and x times the sine of 90 to the calculator. 23 times the sine of 41, boom, 15.08. And I'm also going to need the sine of 90, which is 1. Well, that was handy. 15.089 equals 1 times x, or just x. So that is my answer for this guy. And I'm going to jump down here to number 16, where they've asked me to find the angle x. So now I'm looking for an angle, not the side. So I'm going to go ahead and use the law of sines again, because it's my favorite. So the sine of my unknown angle x is opposite of 7, and the only other angle I know is the sine of 90, which is over 15, because that's what's opposite that. Now I cross multiply. 15 times sine of x equals 7 times sine of 90. And in case you didn't remember, 7 times the sine of 90 is just 1, so 7 times 1 is 7. And I've got 15 times the sine of x. Now this is a little different than the last one because now I'm trying to find that angle. So I'm going to divide both sides by 15 to get the sine x variable part all by itself. And this is what it looks like right now. To figure out what that angle is inside there, I have to use the inverse sine. So on my calculator, I get that from up above the sine button. So I make sure it says inverse, okay? Don't use this inverse for regular sine and vice versa. So inverse sine of 7/15 is 27.81 degrees. And that is what would be the angle for right there. Alright, number 17 will be the next one I do. Let's see, I see two angles of a triangle, so I'm going to just figure out that third angle. Remember, you never trust the pictures. Pictures might be drawn well and might not be drawn well. You just never know. So minus 25 minus 120, that angle B is 35 degrees. Now, I cannot use SOHCAHTOA because this is not a right triangle. So that one's out. So it's either law of sines or law of cosines. Well, let's see. Since I like the law of sines, I'm going to try that first. I know that these two are going to have to be used because I'm supposed to find out what x is. So I know that's got to be part of it. And the only other side I know is the 15 here. So that goes with the 35. So I really did need that other angle. Sine of 35 over 15. Now I cross multiply. So 15 times the sine of 120. And x times the sine of 35. So 15 times the sine of 120 is 12.99. I don't think I'm going to round that. I'll just leave it as 12.99. And then the sine of 35 is 0.5735. Now I'm going to have to divide both sides by that number, 0.5735. Which I don't really want to retype that in, so I am not going to. I am going to just take this number and divide it by that number. And there, now I don't have as much rounding problems. So x, oops, I forgot to look at it. X is 22.64. I'm going to let you do number 18. Alright. Last but not least for Unit 4 Part 2 is number 18 or 19. 18 says the perimeter of a square is 36 meters. Find the length of its diagonal. Make a drawing. Okay, so I will make a drawing. Perimeter of a square. A square has the properties of 4 right angles and 4 equal sides. Now, since there are 4 equal sides and the perimeter is 36, 36 divided by 4 is 9. So that means each side is 9 meters. But the question didn't ask me to find the sides, it asked me to find the length of a diagonal. So when I make a diagonal like this, I actually create 2 right triangles. And I'm supposed to find out what x is. So I'm going to use Pythagorean theorem. 9 squared plus 9 squared equals hypotenuse squared. So I've got 81 plus 81 equals x squared, or 162 equals x squared, or I take the square root of both sides. Let's see, square root of 162, 12.727. And that seems about reasonable if I've got a right triangle with sides of 9. So my answer for this guy is 12.727. Number 19 is for you to do. Alright, for Unit 5 on parallel lines, as I mentioned in a previous section of this video, that parallel lines we had 3 main characteristics that we were dealing with, which were corresponding angles that were congruent. We had alternate interior angles, which are also congruent, and then there was the same side interior, which were supplementary, meaning they add up to 180 degrees. Okay, so as we look at a set of parallel lines, pretend those look parallel, these were the corresponding, these were alternate interior angles here, and then these were the same side interior here and here. Oops, here. Okay, so as we look at this problem down here on number 20, we've got our parallel lines, and these guys are corresponding to each other. Therefore, they are equal to each other. And always when you're doing any types of problems like this, we should be looking for and asking ourselves, what's the relationship between those two angles or those two sides or those two whatever. So since these two angles are supposed to be equal, I'm simply going to solve them algebraically, and oops, that's an 11, and I get x is equal to 16. Now it's tempting to stop there, but I look back and I read the question again, and it says find the measure of each labeled angle. Well, there's only two labeled angles, and it's these two, so that means I must have to plug that 16 back where the x went. So instead of writing 3x minus 11, I'm going to write 3 times 16 minus 11. And that's 48, and that makes 37 degrees. Now the last thing I'm going to do is check 2x plus 5 and do the same thing. And make sure that it also gives me 37 degrees, and it does, which is good. If it gave me something else, I would know I had made a mistake. Alright, the second part of number 20 will be for you to do. You figure out what those missing angles are, and you are trying to target angle X. Alright, so as I look at angle 21, or problem 21, with these three problems, I'm going to let you do those, but I want you to think about what is the relationship between angle 3x and angle x plus 20. Are they equal to each other, or are they supplementary? So I'd remind you to look back at the video part where we talked about that. Then look back at, for the second one, look at angle 2x plus 7, which is this obtuse looking angle here, and angle 109. Are they congruent or supplementary? Then as you look over here, these are not parallel lines. So you're going to have to answer the question, what's the connection between those two angles? Are they congruent? Are they supplementary? Or are they something completely different? But that's going to be your job to figure out. And don't just find the value of x. Find the value of each side. Alright, 22. Okay, 22 has a complex looking diagram, which can be overwhelming to some students. They look at that and all those angles and they just kind of panic a little bit. A couple of the things that I'm just looking at and seeing, there's a little triangle using K, E, and F. There's a bigger triangle using K, C, and B. There's a trapezoid in here, and I know it's a trapezoid because I just now noticed that this line is parallel to this line, and also now that I'm looking for parallels, I see that this line is parallel to this line. So I can make use of parallel properties, I can make use of triangle properties and trapezoid properties. Things I know about trapezoids are that all four angles have to add up to 360 degrees. I know that the triangle has to add up to 180. I know that adjacent angles between the parallel sides on a trapezoid have to be 180. That'll be handy. So there's a number of things that I know about and I'm thinking through already. I'm just going to go first of all and work my way through these angles and figure out anything I can. Where to start? Let's see. I would love to start with some nice simple things like along here, but they didn't give me any numbers along there. this is a little bit yucky looking because it's got 5 things in there. This is not quite as scary because it's got the 125 degrees and then 3 other angles. And I know all the time that as soon as I look for vertical angles, I'm ready to go. These two are supplementary because the 125 and A make a straight angle, so that must be 55 degrees, and that means angle F is 55 degrees as well. Alright, so we're making some progress there. As a reminder, these lines were parallel. So parallel lines mean that I'm going to have corresponding angles. So what I'm looking at with those red lines is, I'm going to kind of recopy it over here, where I've got this line coming across, and this is 55 and that was 125. So that means this is 55 and that's 125 and that's 125 and that's 55. So let's see if I can find angles that fit to that. Yep, here's angle H, 125, angle B is 55, angle J has got to be 55, and this whole green angle right here has to be the same as this 125 because they're corresponding. It's these two that I'm looking at. So I could figure it out that way, or since I know that these guys together here are making a straight angle, 180 degrees, I could subtract the 50 and 55 from 180. Either way, so let's see, that gives me 75 degrees. So that angle has to be 75. Alright, well now I'm cooking along here. This is going fairly well. I just have to figure out how to jump up to these 4. And let's see, I don't have enough in this trapezoid. I'm looking at this kind of blue highlighted trapezoid. I don't have enough to make a sure thing about CD up here. I don't have 2 of the angles down there. I have this feeling that I'm going to need to use those 2 purple lines. So what I'm going to do is take just kind of a sketch over here. I've got 1 purple line and another purple line. Those guys are parallel. One of the transversals I have is this guy right here, kind of slicing across, which makes, I didn't draw it very well, but that says 50. That's between the purple and the black. So that means this would have to be 50, and so would this. And those 2 would be right here and up here if I had drawn it in. So angle C has to be 50 degrees. It doesn't look like 50, but it looks like the same size as whatever that thing is, so I guess I'll go with 50. Now I can make use of the trapezoid that has to add up to 360, or the fact that these 2 have to be supplementary to each other. They have to add up to 180. I'm going to use the trapezoid because that looks cool. So taking away the 3 other angles that are inside the trapezoid, that leaves me with angle D as 130 degrees, which again, it doesn't look like it, but I guess that's what it is. Angle E and D are going to be supplementary, and let's see, angle K has to add up to 180 with that other 2 angles minus the 50 and the 55, and so we get 75. Alright, I don't really care about filling in all those things there. They're in the picture, which is what I really needed. But there are some questions down here about write an explanation for how you found angle C or angle G or angle K. Now some of these can be a little bit tricky to write down, especially because we did it a few minutes ago, but here's what I remember about angle C was I had to find that by looking at this 50-degree angle here. And so unfortunately I don't have any labels on these lines, so I can't really refer to them, but so I'll write as good a description as I can. Angle C is 50 degrees because it is alternate interior congruent with the other 50 degrees because of the parallel lines. And I'm going to just draw a little arrow to them so that I can remember later when I'm reading it, or if this is on the test when my teacher is grading it, so that they can know what I'm talking about. Alright, I'm going to leave the explanation for angle G and angle K to you to write. Alright, number 23 is talking about what does x have to be in order to make the two lines parallel. So notice how they don't have any markings on them to indicate that they're parallel. So my job is to figure out what should be there to make them parallel. Well, the things that I remember about parallel lines is that corresponding angles have to be congruent. So if this was 60 degrees, we would know automatically this is 60. And then these two should match up here. So this has to be 60, and this has to be 60. So now I'm ready for my equation. I've got a 60 degrees, and I've got a 2x plus 10. That means they must be the exact same thing. So 2x plus 10 must equal 60 degrees. So I solve minus 10, 2x is 50, x is 25. Now I'm going to just plug that back in and make sure that it really works. 2 times 25 plus 10, that's 50 plus 10. Yep, that worked. That gave me the 60 degrees that I wanted. I'm going to let you do this one and this one. And I want you to ask, what can I fill in? What can I figure out from the picture? What has to be congruent? And write an equation for it. Okay, 24 is one that I'm going to do part of. I'm not going to do all of it. Plotting the points is something that you should be good at. There's no numbers on this, so I'm just going to assume it goes by ones. So this would be at 4, and negative 7 is way down here. Unfortunately, it's off the picture. 1, 2, 3, 4, 5, 6. Yep. Too bad about that. So that's point A at 4, negative 7. Remember, you go the x direction first, then the y direction. So for point B, the x direction is negative 6, the y direction is 3. 1, 2, 3, 4, 5, 6, and 3 would be letter B. And we are to draw AB, segment AB. So there we go. Drew segment AB. Check. Find the midpoint of AB. Now the temptation for a lot of students is to just eyeball it and say, that looks like about the midpoint, so I'll just call it there. That's not a bad place to start, but that's not good enough to be absolutely sure. The midpoint, the technique that we used for finding that is to add the two x coordinates and divide by 2. What we're really doing is we're taking the average of the x coordinates and the average of the y coordinates. So on this problem, the x coordinates were negative 6 and 4, and the y coordinates were 3 and negative 7. And we divide each of these by 2, and we get negative 2 over 2 and negative 4 over 2, which is negative 1 comma negative 2. Which is in fact right there, right where we thought it was. So the reason to do this is to verify what our eyes told us. Our eyes said, I think it's there. Our brain said, I think it's there. We have to actually figure it out. Letter C says find the length of AB. The length means I want to do the Pythagorean theorem. And I'm going to make use of the right triangle that I can see that connects from point B to point A. Something like that. Now you can use the distance formula. If you remember the distance formula, the distance formula is just the Pythagorean theorem, but if you like the distance formula, use that. If you don't remember it, use the Pythagorean theorem. So I'm going to let you figure that out. The slope of AB, we did just talk about slope in a previous part of this review, so I would ask you to go back and review that, but remember that it is dy over dx, or the change in y over the change in x, and you should end up with a negative number for this, because it is going down and to the right. Excuse me again. Letter E and F are about parallels and perpendiculars. So I want you to go back to the previous part of the video where we talked about that and review those as well. In Unit 6, we did constructions with a straight edge and compass, and you will have to do at least one of the following ones on the final exam. So you should review how to do these. Now, chances are, if you're watching this at home, you probably don't remember, or you probably don't have a compass with you or a straight edge, but I'm just going to briefly go through the procedure, the process that we do to make these constructions. So for this one, you'd start with the point of your compass here and the other side on B, and kind of draw an arc this direction and this direction, and then reverse it. Put the point down here and the arc here, and you draw another one, and the connection between these two creates a line that is both perpendicular and it bisects it. Even though my picture rough sketch doesn't look like it, it does. And in fact, that's a handy way to make isosceles triangles. You pick any point on this line, this is going to be an isosceles triangle. You pick a different point, also isosceles. So it's a way of making equidistant things using compass and straight edge. The angle bisector procedure was to put the point right on letter C and draw an arc that kind of covers, just pick any random radius that, as long as it hits both sides of the angle, that was good enough. Then you move your compass over here, put the point, stretch the pencil out so it reaches here, draw a curve, and you can even keep it going if you wanted, and then reverse it, put the point here, and draw a curve that direction. And what you'll find is that this point and this point will go right through the middle of the angle, and it will split the angle into two congruent pieces. The regular hexagon, this is number 27, what you would do is start by putting the point right here at letter D, stretching your pencil to point O, and then drawing a curve right here. So that what we've done now is we've made an arc, we've made a segment that's the same length as the radius of the circle. Then you move the point to this point and do it again and connect those two, and then do it again and then connect those two, and rinse and repeat all the way around until you get yourself a nice regular hexagon. For number 28, construct a square inscribed in the circle using point D. I think we mean maybe point A, but who cares? This point right here. One of the key ingredients of a square, and this is how it was easiest to make squares, was that the diagonals of a square were both perpendicular, congruent, and bisected each other. So I would start by just using my straight edge and drawing a line straight across there, and mark that point, mark that point. Then I would do the exact same construction we did over here, where the perpendicular bisector, I'd put the point of my compass on A and the other point over here, or the pencil over here, and I would mark out an arc that would go this direction, kind of go through there and that direction. And then I would reverse it and do the same thing, so that I would get a perpendicular bisector going right through the center of the circle. And then this point and this point will be the other two vertices of my square, and I would have, boom, a square, which that doesn't look like, but that's okay. Alright, in Unit 7 we did quadrilaterals and parallelograms. Number 29 says put a check mark in the appropriate box if it applies to the quadrilateral. So I'm going to just kind of off to the side of these sketch what a parallelogram looks like. And for here I'm just talking about the generic any kind of parallelogram. The kite has to have two congruent adjacent sides and two other congruent adjacent sides. That was a key ingredient of a kite. Trapezoids looked something like this. And there was also isosceles trapezoids, where those two non-parallel sides were the same. Rectangles, most everybody knows that pretty well. Rhombus kind of looks like a diamond shape where all four sides are equal, but the angles aren't necessarily equal. And then of course everybody knows our good friend the square, four congruent sides, four congruent angles, and the rectangle had four right angles. So opposite sides congruent, that fits the parallelogram, the rectangle, the rhombus, and the square. trapezoids don't have opposite sides congruent. They might have some sides congruent, but not always the opposite ones. A kite doesn't, because they're not opposite, they're adjacent to each other that are congruent. At least one pair of parallel sides. Well, a parallelogram has two pairs, so it definitely has at least one. A trapezoid has only one pair, but it has at least one. Rectangle, rhombus, and square all fit. The kite is the one that does not fit because it doesn't have any parallel sides. Two pairs of parallel sides, that's parallelogram, rectangle, rhombus, square. Diagonals bisect each other. Now this can be tricky for students because they look at something and think that they do bisect when they don't necessarily. Like the trapezoid definitely does not. The parallelogram does bisect each other when we draw those in. These are the same, these are the same. Now they are not congruent diagonals, but they do bisect each other. The kite, one of the diagonals gets bisected, but not both. So the rectangle, rhombus, and square all work. Diagonals are congruent. That only happens on a rectangle and a square. Diagonals bisect the angles. That only happens on a square and a rhombus. And those are hard to see. I would sketch those out and look at those myself again just to make sure. Perpendicular diagonals, well, the kite actually has perpendicular diagonals. The rhombus does, and so does the square. Four right angles would be rectangle and square, and that's it. All right, moving on for number 30. Which of the following is not a type of parallelogram? Please make sure when you're doing the final exam that you read the questions carefully. I often have students that will come to me and say, I don't understand. All of these are types of parallelograms. And the question is all about what is not a parallelogram. And out of all of these, letter C is the only one that's not, because it only has one pair of parallel sides. Parallelograms have to have two. All right, I'm going to let you answer 31 through 33 as we move on to Unit 8. Okay, so for Unit 8, polygons, which is the unit that we just recently did, number 34 is about matching to different parts of the polygon, and I think you should be able to do that on your own just by reasoning out what the words mean. For the regular pentagon shown to the right, do the following. Find the measure of a central angle. Well, this pentagon has 5 sides, like every pentagon does. So a central angle would be 360 divided by 5, because even though I didn't draw them all, there would be 5 congruent isosceles triangles from this thing. So that's going to be 72 degrees. That is letter A. Letter B, the measure of one exterior angle. Well, all the exterior angles in every polygon add up to 360. Since there are 5 exterior angles, that is also going to be 72 degrees. We should see that this is always the same, especially when we're talking about regulars. The measure of one interior angle, well, an interior angle and an exterior angle are related to each other, so that should be 108 degrees, because 72 plus 108 equals the 180. The sum of all 5 interior angles, well, take 5 times 108, we get 540 degrees. Or you could use the formula which said if there are 5 sides, then there would be 3 triangles, and for those of you playing along at home, those would be triangles using these blue lines like this. I get 1 blue triangle, 2 blue triangles, 3 blue triangles. That's where the 5 minus 2 comes from, times 180, which is still 540. Same answer, different technique. Sum of all 5 exterior angles, well, the cool thing is they always add up to 360, so it doesn't matter. And then last is to find the area of the pentagon. So what I normally do is I draw the one isosceles triangle that's represented from the original picture, where that was 72 and this was 10 centimeters, and that of course means that this is going to be 18 degrees out here, and 18 degrees, take it back. Okay, I need my calculator. No, I don't. There's 108, there's going to be 54 degrees. 54. How about that? That's more like it. Alright, so then I split that right triangle up, that isosceles triangle up into the apothem, or the height, and this will be 5, and this will still be 54 degrees, and this angle here will be 36, half of the 72. Now you can use SOHCAHTOA, you can use the law of sines. I like the law of sines, so I'm going to do that. The sine of 54 degrees over the height, or the apothem, equals the sine of 36 degrees over 5. So we've cross multiply by taking 5 times the sine of 54 and the height times the sine of 36, and on the calculator I want to make sure that I'm in degree mode, and I am, so that's good. So now I take 5 times the sine of 54, that gives me 4.045, and over here the height times the sine of 36, 0.5877. Now I'm going to have to divide both sides by 0.5877, both sides. So on my calculator, I don't want to retype all that, so I'm just going to go up and copy the 4.045 and then divide it by that. I could have just retyped it using sine of 36, but that's okay. So I get the height is 6.88. Now that's the apothem, or the height of the triangle. So my area for the whole polygon is going to be the 5 times the area of the triangle